What's up, guys? It's Dr. J. I'm back in the workroom, okay? And today we're going to talk about energy, all right? Let's roll. Okay, so energy itself is defined as the capacity to do work, all right? And that makes intuitive sense, right? You're not getting a lot done on days when you feel like you have low energy, okay? And, it always takes a lot of energy to get anything significant done, right? So that's what energy is. It's the capacity to do work. And there are two types of energy, and we're going to discuss both of them. Okay, and so the first type we'll discuss is potential energy. And so potential energy is stored energy that could potentially be released, okay? And there are a few different types of potential energy, but we're going to focus on one in particular, and we'll do that in a little bit. But first, let's talk about the second type of energy. Okay, so the second type is kinetic energy, and that's the energy of motion, or we could say that moving objects have this energy, all right? And so we can go ahead and mathematically quantify these two types of energy, and we're going to be very specific with the type of potential energy that we're discussing, okay? So we'll start with potential energy, and we'll get a little math going for this guy. Okay, so when we talk about potential energy, what we're really talking about is gravitational potential energy. And gravitational potential energy is just abbreviated as PE. And the mathematical formula we use for determining any object's gravitational potential energy is this one. So PE equals mgh, all right? So just multiplying on through. M stands, of course, for mass, okay? And we use kilograms. G stands for gravitational acceleration. Okay, gravitational acceleration. And the units, of course, are meters per squared second. Okay, and then times height. Okay, height. Okay, and this is in meters. Okay, and potential energy, of course, is in, oh, you don't know this yet. The unit for potential energy is J, joules. Okay, so this is the unit for potential energy, named after a guy named Joule. Okay, so joules. Kinetic energy is defined a little bit differently. So we're going to talk about that on the next panel. All right, so I'm going to go ahead and clear this off, and then we'll talk about kinetic energy on the next panel. So any object's kinetic energy, and I'll just use KE and PE. I don't think I'll use the periods there for the abbreviation. KE equals 1/2 times m times velocity squared. Okay, and so kinetic energy, of course, is in joules. Mass, okay, m is, of course, mass in kilograms. And velocity is in meters per second. Of course, we're going to square to get meters squared per second squared. So if you do the math on through, 1 joule is equal to a kilogram times a meter squared divided by a second squared. Okay, and so the math does check out. And so those are our formulas, right? And so we're going to go ahead and have a little bit of practice putting those formulas into action. Okay, so here's our first problem. Find the potential energy of a 45.5 gram golf ball that is 4.9 meters above the ground. Okay, and if those numbers look familiar to you, they should, right? Those are values that we measured or otherwise used in our lab earlier in the year. So we're looking for potential energy, right? We're looking for potential energy. And so we know the potential energy is equal to mass times gravity times height, okay? And so the mass in this case is 45.5 grams. We're going to move to kilograms because we want to be able to use joules. So you divide by 1,000. So 0.0455 kilograms times gravitational acceleration, which we just know. We know that that's 9.8 meters per second squared. Okay, that's G. Times the height, which is 4.9 meters. Okay, and when we multiply all that out, we get 2.18 joules, okay? 2.18 joules. Okay, and really, for significant figures, since I've only got a height of 4.9 meters, I should go with 2.2 joules, okay? Because I only get two significant digits because that that value is only good to two digits. So 2.2 joules are what I get, okay? So, all right, so that's the potential energy, right? And so what about kinetic energy, right? Because when we have a golf ball and we hold it above our railing, that is indeed 4.9 meters high, well, what do we always do, right? We drop the golf ball, of course, because it's fun and informative. We get to learn something, collect some data. So, okay, what about the kinetic energy? What are we going to do with this, all right? So let's find out. Here's our second example. We want to predict the velocity of that golf ball as it hits the ground, okay? So how are we going to do that? Okay, so we know that kinetic energy is equal to 1/2 times mass times velocity squared, right? But here's the trick. Here's the really important thing. Once some object, right, that initially only contained potential energy, okay, once an object that only initially contained potential energy falls its entire height, okay, falls down to the ground, that means all of its energy has become kinetic energy. And so the energy that we calculated here, that's the energy that the golf ball is going to have upon impact with the ground. So we can say that this kinetic energy is equal to 2.2 joules, okay? So all we have to do is solve for V because we already know what mass is, right? So 2.2 joules, right? And I'll go ahead and, yeah, I'll see that like it is, 2.2 joules, okay? That equals 1/2 times 0.0455 kilograms times velocity squared. So we're gonna have to solve for velocity, right? So let's go ahead and do the math out. We're going to multiply both sides by 2, and we're going to divide both sides by 0.0455. And I'll show you what we get in just a second. All right. So if we multiply both sides by 2 to get rid of this 1/2, we get 4.4 equals 0.455 times v squared. If we divide both sides by 0.0455, we get 96.7 equals v squared. And then if we take the square root of both sides, we get that v is equal to 9.8 meters per second, okay? So that's how fast we should expect the golf ball to be traveling when it hits the ground, okay? But if we perform this experiment, and we actually watch this golf ball hit the ground, okay, you know, what value are we going to get, right? Like if you drop a golf ball, will it really hit the ground with that much velocity, right? And then even if it does, right, how much energy is the golf ball going to retain, right? What's going to happen after it hits the ground? How high up is it going to bounce? Is it going to bounce all the way back to where we released it? Will it somehow bounce higher, right? Those are things that we have to figure out in the lab. See you there, everyone. Until that time, good luck, and may all the forces be with you.